SNARKs for P and batch NP from LWE. I should warn you front that LWE is not going to show up anywhere in the talk. So the talk is really about SNARKs from some standard assumptions, right? Okay. So the main object we are interested in is a form of non-interactive argument where the prover and verifier hold an instance from some NP language, and the prover wants to convince the verifier that the statement is in this language is true. We want the standard completeness and soundness properties. Completeness says that if X is true, the verifier should accept, and soundness says that if X is false, then the verifier should reject. And in this talk, we are interested in computational soundness, which is why we are talking about argument systems. So soundness only holds against PPT provers. On their own, these objects are fairly easy to build, right? The prover can just send a witness to the verifier, so that is not very interesting. So usually we equip non-interactive arguments with some additional properties, and the main property that we are interested in is succinctness, which essentially requires that the proof size and the verification time should be much smaller than the witness length. Here, the representation is for Turing machine modeling, but the same intuition applies. So these objects also, the way I modeled it on the slide, they are not really possible in the plain model. So we usually equip the prover and verifier with something extra. In this talk, we are interested in equipping them with a CRS, a common reference string, which ideally should be from the uniform distribution, but could be structured as well. Okay. So in this talk, I am mainly going to focus on one question. Okay, so I skipped a slide. Sorry. So let me first try to convince you, why we care about these objects. All these motivations are fairly obvious. First and foremost, these objects are fascinating to build, mainly because of this seemingly strange succinctness requirement. The fact that we can achieve them is quite intriguing. If you have watched Yuval's talk at a previous Simon's workshop, you can see, hopefully you're convinced that there's a strong interplay with theoretical computer science here. And as far as applications are concerned, we all know about applications of SNARKs to blockchains. And perhaps the statement at the bottom here is a little bit controversial to some, that SNARKs, especially when equipped with zero knowledge, have probably now overtaken even FHE in popularity. If you go to a random meetup group, especially in the Bay Area, you are likely to hear non-academics excitedly talking about SNARKs, even if they don't really understand the details. I've done that, so yeah, you can take my word on it. Okay, so in this talk, I'm mainly interested in one question, which is what assumptions can we build SNARKs from? Okay, and the talk is really not going to focus, unlike the last talk, it's not really going to focus on concrete efficiency. We are just interested in asymptotics, and most of the talk is going to focus on the present, right? So in true spirit of mindfulness, but I will talk some about the past and a little bit about the future directions as well. Okay. Okay, so let's talk about what we knew about SNARKs for NP. This is circa 2019, roughly. Okay, so perhaps the most famous result is SNARKs for NP in the random oracle model, which we know from the work of Micali, which essentially takes Killian and then collapses it using random oracles. And we can obviously instantiate it using some concrete hash function like SHA-256 and get heuristic security. The other very popular line of work is to build SNARKs from knowledge or extractability assumptions, right? And this is a really, really long line of work. Perhaps I stopped at 2016. If you look at the works beyond that, it's manifold times in number. And I should say that many of these schemes are very concretely efficient. They're implemented, used in practice, and there are many startups emanating from this line of work. From a theoretical perspective, you could argue that it's perhaps a little bit unsatisfactory. For one, the assumptions used here are non-falsifiable in the sense of Moni's definition. If you think about the reduction as a subroutine, sorry, as an algorithmic construct, then there is a missing subroutine in that reduction, right? Which is the assumption that there exists a small extractor, right? And you can also kind of think it a different way, that you are building an extractor, assuming an extractor, right? If you draw an analogy from the line of work in non-malleable cryptography, there also sometimes we have the scenario where you can assume non-malleability of some weak form to build non-malleability of a stronger form. So, okay, so that's so this is what we knew. So what we are interested in is using more standard assumptions. So there is a big barrier, which is very well known. The work of Gentry and Wicks showed that if you want SNARKs for NP, then with some caveats, it's going to be highly unlikely if you want to build them from standard / falsifiable assumptions. Okay, so I'm going to ignore the caveats right now and just go on believing that this is the end of the story, that it's impossible from standard assumptions. I'll revisit this towards the end of the talk. Okay. Okay, so now if we have this impossibility and just treat it as an unconditional impossibility result, then we are left with sort of one natural question, which is, can we build SNARKs for subclasses of NP, some interesting subclasses of NP from standard assumptions? Okay, and this is what the talk is going to mainly focus on. And I'm going to focus on two subclasses in particular. The first is very natural, polynomial time computations. Okay, which is essentially the scenario where a client has delegated some computation to some server, and the server wants to convince him that he performs some polynomial time computation correctly, and the verification time should be much smaller than the time it takes to compute. And this object itself has many many important applications in cryptography. Listed some of them here. The second class that I'm interested in is SNARKs for batch NP. So this is a structured version of NP where the prover is trying to prove, let's say, k instances to the verifier, and we want that the proof size should be much smaller than the total witness length, which in this case is k times the size of one witness. Okay, and the verification time should also be correspondingly smaller, except that the verifier will have to read the instances once, but that's about it. Okay.
Do we have to prove that all of them are
yes.
at the same time? Okay.
Yes. You can consider some generalizations, but for this talk, yeah, I'm interested in the AND case. All the instances are true. Okay. So
why is it the polling?
Yeah, it doesn't need to be. It's just generally, yeah, written more generally, but yeah, not usually. Good. So batch NP is itself a useful tool for building other applications as well. In fact, even before people looked at SNARKs for batch NP, batch verification, for example, was studied in the setting of signature schemes and other primitives. Okay? But you can use SNARKs for batch NP to also build aggregate signatures. Okay, so why am I talking about these two particular classes? Well, first and foremost, Gentry-Wicks lower bound doesn't apply here. Okay. At a technical level, some connection between these two subclasses was already made in prior works of Yaels, Vika, and Justin, and some follow-up works. In this talk, I will show a more formal connection, and this was also established in another work recently. And one takeaway message should be that SNARKs for batch NP are sort of a very good workhorse for building other kind of SNARKs and other things. So that will be one message from this talk. Okay, so now if we focus on just these two subclasses, P and batch NP, then we can look at what was already known in this setting. And there are sort of two categories. So one line of work, very interesting line of work initiated by KRR in 2013 was looking at the setting where the verifier holds a secret key for verification. So this is the setting where, along with the CRS, you sample some secret verification key that is given to the verifier. So only that verifier can verify proofs. And in this setting, you can actually build such succinct proof systems for P and batch NP, and even some other related classes based on standard assumptions. But the setting that I'm interested in for this talk is the public verification setting where there's no secret verification key. Anyone can look at the proof and verify. And here, essentially, we were in two sort of settings. Either you can use obfuscation style assumptions, obfuscation, or even multilinear maps, or some non-standard assumptions in bilinear map setting. but essentially, so I'm cheating a little bit here. Standard assumptions. If if IO is from standard assumptions, then maybe this question comes with an asterisk. But let me redefine standard as meaning LWE or bilinear maps, just something of that sort, right? Okay, so this is the main question: can we build SNARKs for P and batch NP from standard assumption? Okay, so.
Just a question about the models. What about adaptive soundness and the...
Yeah, so I did not talk about adaptive versus non-adaptivity. The soundness will be adaptive. For P, it will be fully adaptive. For batch NP, it will be semi-adaptive, which maybe ask me again later, and I'll point you when I won't talk about the exact adaptivity model, but you can,
because Gentry-Weeks, for instance, doesn't apply.
Right, good. So for P, it will be fully adaptive. And for batch NP, it is essentially the most adaptivity you can hope for, beyond which it starts applying, the Gentry-Weeks thing starts applying. Yeah. I know. It's because of the known transformations, from prior works, that if you have fully adaptive batch NP, with the argument of knowledge property, which the work does achieve, then you can convert them to SNARKs for adaptive SNARKs for NP. This is something from BHK.
Also, SNARK with designated verified SNARKs, as you're saying.
That doesn't matter. I mean, they showed this transformation in the designated verifier setting, but the same thing applies in the public verification setting as well. So again, I'm saying that if you have SNARKs for batch NP with full adaptive soundness and also an argument of knowledge property, then you can take that, throw in some additional machinery, and you will get SNARKs for NP with adaptive soundness, which would violate, some hash functions.
Is the knowledge property an issue? Do you get it for the batch?
For our results, we do get it, yes.
So somehow when you have only slightly less adaptive security, then it does not have any consequence in the...
No, then it doesn't have.
But your construction only gets local extraction, right?
That's true. Yeah. So for the adaptivity that we defined, it makes sense. But yeah, you're right. I am cheating a little bit here by there are various flavors of
Right. But this one is not sufficient for the implication.
That's true.
Right?
Yeah,
so
that's true.
May not even rule it out, even if you had adaptive security.
Is the extraction?
I am cheating a little bit.
Yeah,
Yes.
it's a weaker extraction.
More stuff for the future work, right?
The way you say it sounds very, if you have cooked up your head,
I don't actually. Yeah. I can try to reconstruct it, but yeah.
Construct a model tree using the witness and then do a delegation scheme or something. I don't recall that. You made a delegation scheme and the battery and essentially commit to the witness using the and
We can discuss later. We can reconstruct it. It's not, it's not very complicated from what I briefly remember. Okay. So again, so this is the main question. So I'm going to talk about two results, both from the same work, which is that we can build SNARKs for P from LWE. The parameters are asymptotically essentially what you would want, right? Everything is polylog in T, so in the Turing machine model. And then for batch NP also, it's essentially the parameters that you would want. Later, I will, towards the end of the talk, I'll mention even stronger requirements potentially in terms of future work. But these are the two results. Okay. So let me then just jump to background. And the main sort of starting point for these works and a lot of work in cryptography in the recent years is essentially looking at revisiting the Fiat-Shamir paradigm and then trying to instantiate the random oracles in that paradigm using concrete hash functions. Okay, so let me just recall what is Fiat-Shamir. So it's essentially a technique for round collapsing public coin interactive protocols using random oracle. So if you start with, let's say, a Sigma protocol, then you can apply the Fiat-Shamir heuristic, which says that instead of the verified sampling a random challenge interactively, the prover can just compute the random challenge as applying the random oracle on the first round message. So this is for 3 rounds, but you can generalize it for more round protocols. And now the prover can just compute the entire transcript in one shot and send it out, and the verifier can check for correctness. Okay, so this can be proven sound in the random oracle model. And now the natural question is, if we want to obtain a result in the standard model, where by standard I mean that let's say we use a CRS and then get rid of the random oracle, then we can already ask the question, can we instantiate this random oracle with maybe some particular hash function family? And we know that there are some negative results in this direction. So if you want to apply this paradigm for general arguments, there are some explicit counterexamples, albeit contrived. And even in the setting of proofs, there are some partial negative results. On the other hand, there was a possible route, suggested in some early works via this notion of correlation intractable hash functions. And this is the notion that I'm going to talk about, which is going to be the central player in obtaining positive results. So let me define correlation intractable hash functions. So it's essentially a family of hash functions, keyed hash functions, which are associated with some function class f. So I should say I'm giving a simplified definition where I'm defining correlation intractability with a function class. You can generalize this relation, this definition to hold for relations instead of functions. So again, the idea is that we want that any PPT adversary should fail in the following experiment, where you sample a key from the key space at random, and then the PPT adversary is supposed to output a value x, such that when you apply a hash when you compute the hash over this value x, what you obtain is actually the output of f on x. And you want that the probability that this happens is negligible. Again, if you want to generalize it for relations, then what you would want is that the probability that the relation when it takes as input x and h of hk of x, it accepts. Right? So this is the notion of correlation intractable hash functions. And now suppose we have such hash functions. Okay. Then let's try to see how we can use them to actually instantiate the random oracle in this Fiat-Shamir paradigm. So now let's say we sample a key for correlation intractable hash functions, and I haven't defined what is the function class f yet. I will in a moment. But let's say we sample a key from this family of hash functions, and that's a part of the CRS now, which is given to the prover and the verifier. And now the prover works as expected. It will just compute the challenge as the hash of the first message, and then computes the response, sends it to the verifier. The verifier can also recompute the challenge and then just check for the transcript correctness. Okay. So the question is, why is this sound, right? Okay, so here is the idea. And again, I'll consider the simplified case where the protocol that I'm starting with has two special soundness, which is basically saying that if I give you 2 accepting transcripts with the same first message, then you can extract a witness. Okay, so in other words, what I'm asking is that for any alpha, that is the first message, there is a unique beta that can lead to an accepting gamma. Okay, so you can see that the special soundness implies this property, right? Again, when x is false, right? When the statement is false, then for any alpha, there is a unique beta on which you can find there even exists an accepting gamma. Okay. Okay. So now I can define a function, this mapping from the first message of the protocol, that is alpha, to this bad beta, right? The bad challenge for which there could exist an accepting transcript. Okay, so I'm calling this function as bad function. Okay. And now I'm going to basically consider correlation intractable hash functions, which are correlation intractable for these bad functions. Okay. And now if we look at this transformation, we can argue soundness as follows. So if a cheating prover does output an accepting transcript, right, for a false statement x, then you can see that first of all, by definition, the challenge beta is just the output of the hash. But at the same time, because the way we define this bad function, right, we have that beta is also the output of the bad function applied on alpha, right? So now you have that basically the output of the hash is equal to the output of the bad function on the same alpha, and this contradicts correlation intractability. Okay, so this is how we get soundness. Again, this is for the simplified case. The idea can be generalized a little bit. I'm not going to get into too much details of how some of the generalization works. It's yeah, there are some subtleties that show up, but for the purpose of illustration, this is good enough. Yeah. Okay. So now we have roughly a general recipe to building various kinds of non-interactive arguments, which is design again non-interactive arguments with potentially different properties. So you start with an appropriate sigma protocol. Again, appropriate depends on your application. Then you construct a CIH hash function, which is correlation intractable for, again, the appropriate bad relation defined with respect to the sigma protocol. And then you marry them together, right? So I should say that even though we don't care about zero knowledge in this talk, the previous transformation does preserve zero knowledge. And in fact, this was sort of one of the important motivations for this line of work, right? Okay, so let's talk about existence of correlation intractable hash functions. So this is a very partial list. There are many other results using various other assumptions like IO and so on. But in terms of using LWE, we have really nice results. So we can obtain CI hash for polynomial size circuits. So bad functions described as polynomial size circuits. And then there's also, for the purposes of this talk, what is even more relevant is the more recent work of Justin, Alex, and Ron, which shows how to build CIH for a particular class of sparse relations, which is this efficiently verifiable product relations. So, which is very useful in protocols where you're doing parallel repetition. Okay. And you can also build CI hash for some smaller classes using sub-exponential DDH. Okay. So, so I should mention that while we are interested in this talk in achieving succinct non-interactive arguments using this paradigm has been very successful over the recent years for various objectives. Perhaps one of the more popular ones has been in building non-interactive zero-knowledge proofs from new assumptions, including the breakthrough work on building NISICs from LWE, right, which was resolved using this approach. And there have been many other applications as well. So the natural question is, right, that can we now use this paradigm also for building SNARKs? And we can again just look at that recipe, the general recipe that I mentioned earlier, and then just try to tweak it in a natural way, right? So instead of starting with an arbitrary sigma protocol, we should start with a succinct sigma protocol because the transformation doesn't really compress, right? It just preserves the communication. And then the rest of the steps should be hopefully be the same. Okay, so that's the starting point. So one very natural candidate, starting a succinct interactive protocol is, for example, Killian, right? It's not even just P and batch NP. It's in fact a succinct argument for NP, right? And we can ask whether we can just apply this approach to Killian. In fact, if this could work, it would not only give us SNARKs for P and batch NP, but maybe even all of NP. So the sort of the main challenge with this approach is that Killian is an argument system, right? It's a succinct argument system, whereas the CIH line of work has essentially it essentially works when you start with an interactive protocol, which is a proof system, a statistically sound proof system. Okay, there is perhaps one exception to this, which I haven't mentioned here, but this is the main story. So now we can ask, okay, is there any hope to applying this approach to argument systems? And you can at least see some problem right, in trying to do this. So first of all, the known constructions of CI hash, support sparse relations, which essentially means, that the starting protocol should be statistically sound, right? Because what does a sparse relation say? It says that for every alpha, right, there's only few betas that can lead to accepting gammas. Whereas if you think about argument systems, the problem is that for every alpha and beta, there could be an accepting gamma. It's just that it may be hard to find, right? So it's not clear how to apply this approach to the setting of arguments, at least in general. So now we can ask, okay, fine, let's give up on arguments, maybe. Let's go to the setting of proofs again. And do we have good starting interactive proofs that are succinct? So here we are very limited in what good starting points. So one starting point is the well-known GKR protocol, and indeed which essentially gives you bounded depth succinct interactive proofs. And this is essentially what was used in two recent works that I had intentionally not mentioned earlier. Basically, these works by Canetti et al. And then more recently by Jutla et al., which essentially take GKR and then show how you can apply the CI hash framework on this protocol to obtain SNARKs for bounded depth computation. The only other really candidate that we know, a good starting point, would be the work of RRR, which gives you bounded space computation. But if you want a protocol which is for all of P and succinct, well, yeah, that seems unlikely based on what we know. And if you think about batch NP, it's not like there are any fundamental barriers that I'm aware of. It's just that we don't know how to build succinct interactive proofs for batch NP. For batch UP, we do know some protocols, at least with sublinear communication. Okay, so then the question, we are basically exhausting all options one by one. So now the final question remaining is that, can we apply this framework by somewhat relaxing our soundness requirement? Maybe we don't need full statistical soundness. Maybe we can do with something weaker that is still sufficient for this approach. And that's essentially what I'm going to now talk about. So I'm going to give a definition for the case of batch NP. So I'm going to define a notion of interactive arguments for batch NP, which have two modes, and there will be statistical soundness in some cases and not in the other cases. Okay, so that's the general idea. So again, we have the scenario where we have a prover, a verifier. The prover wants to prove that case statements are true, and in the normal mode, so there's a CRS which can be either in the normal mode or it can be in a trapdoor mode. And in the trapdoor mode, the CRS can be programmed on an index. Okay, so this index I can be from 1 to k. Okay? And the requirement is that if the CRS is in the trapdoor mode programmed at index I, that then any statement that the prover will prove at the ith index, right? So there you will have statistical soundness. Okay? So if the statement is false, the statement that the prover is proving at that index I, if it is false, it will be caught. Okay, even if the prover is unbounded.
Do you really need the normal mode? Can it be like the trapdoor mode with I equals, I don't know, like?
Sure. I mean, yeah. I mean, I guess you can define it that way. Yeah.
Difference, right?
Sorry.
There isn't really a qualitative.
Yeah, probably not. Yeah.
So is the normal mode CRS?
I mean, it is a random string.
It's just a random string.
Okay, so that's
Yeah. So in that sense, it's the distribution. Yeah, can be nicer. Sorry. Yeah. Okay. And for most of you, it should be easy to see that this notion is essentially inspired by somewhere statistical binding commitments, right? Which is this notion of hash functions / commitments, where you have a succinct commitment of a vector, and you can still be statistical binding at one or more location. The commitment size or the hash size grows with the number of indices where you are statistical binding. So now let me just illustrate very quickly why is this notion useful, why it can help get around this issue of applying the CI hash framework. So the idea is fairly natural. if you want to prove correlation intractability, you want to start with something. You want to start with a proof which is statistically sound, right? So here we can rely on the structure of the batch NP, this language. If the statement overall batch is false, then it means that there is at least one index I, some xi, which is false, right? So we can, program the CRS at index I. Now we have statistical soundness, and now we can actually apply the CI hash framework, right? All we wanted is to, start with statistical soundness, and this allows you to do that, right? Yeah.
Maybe it was Rachel asked towards the beginning, like you're saying or and, can you do or? This feels like very empty, right?
So the thing is that good. So it is and. The thing is that or is easy in the sense that in or there's already a short witness, right? I mean, now you can ask, okay, combinations of then yeah, that's a whole different question. And there, I mean, we don't prove anything in this work, but I would conjecture that some extensions should work. It's just that again, or on its own is not interesting unless you want a zero knowledge property, right? Because in or there's already a short witness. You just maybe want to hide which of the which of them is true.
So the designated verifier setting,
the extensions that are known. Yeah. So what about what we know the saying is that in the designated verifier setting, there are some extensions known from from batch NP to some
monotone circuits, which is what you would expect.
Monotone circuits, and I believe that the same should work here as well.
What I was saying is this feels like it really relies on the properties of and.
This yes, but again, you can use the ideas to.
Like you can do and, so maybe
you can do or trivially, you can do and trivially.
Okay, good. So now that we have moved past this issue of what is the right starting point. So our starting point is going to be dual mode or somewhere statistically sound batch arguments, whatever you want to call them. So the first step will be now to build these objects for all of NP in the interactive setting, right? Once we have them, again, you can apply the CI hash transformation. For our particular scenario, we will need CI hash from the work of HLR. So this transformation is something I'm not going to talk about. It works along expected lines. It's just that we need to use these particular CI hash just because of the design of our interactive argument system. And then the second step is once we have SNARKs for batch NP, then I'll talk about a general transformation to go from this object to SNARKs for P. Okay. So actually, in the presentation, I'm going to switch the order. So I'm first going to talk about the general transformation, convince you that batch NP are useful for SNARKs for P, and then I'll talk about the construction. Okay, so let's look at this transformation of going from SNARKs for batch NP to SNARKs for P. And even this transformation, I'm going to simplify it to the scenario where P is actually bounded space computations. There are general, general tricks using Merkle trees, etc., to go from bounded space to. So how would we try to use batch NP if I want to, prove to you actually correctness of some polynomial time computation? So here is a very natural idea. I look at all the steps of the intermediate steps of the computation, the P computation. So let's say some T steps are there, right? So I write down all of these states of the Turing machine, right? So ST1 to ST some capital T. And now I can create a batch of statements. So what is the batch of statements? It's saying that, look, I went from the first state to the second state, this is a valid transformation. Then from the second state to third state, this is a valid transformation, and so on and so forth, right? So now I have a bunch of statements, and I can try to use a SNARK for batch NP to prove the correctness of this polynomial time computation, okay? So that's a very natural starting point. And so I'm obviously omitting lots of details here, and I'll come to that in a moment. And now in terms of arguing security, I could hope to again do the natural thing. First I will try to argue that the first step was actually correct by using the soundness of SNARK for batch NP, right? Then I will argue that the second step was correct. Then I'll argue the third step was correct, and so on until I reach the end. And hopefully I've established that the entire sequence of computation was correct. So that's essentially the hope, what we would like to do. This doesn't quite work for various natural reasons. So the first thing we have to address is that if you look at the size of the number of instances for this batch NP language, well, that's essentially capital T, right? Where T is the runtime of the Turing machine, right? And the problem is that for batch NP, right, the verifier must read all the instances. And if he reads T instances, well, then the verifier is already running in time in T, capital T, which is something we don't want. Okay, so we need to solve the problem of number of instances, and the way we are going to solve it is by using basically SSB commitment with short local openings. So basically, we take all of these states, we commit to them using SSB commitment, and now my new instances will essentially be that. So I'm just going to prove that for every I, right? I have two states, STI and STI plus 1, and their corresponding SSB openings. And I will prove that A, the openings are valid, right? So they are accepting, and that the transition from STI to STI plus 1 is also valid. Okay, so now what are our new instances for this batch NP language? Well, it's basically just these indices, right? It's basically the first instance is index 1, the second instance is index 2, and so on, essentially, right? Okay, so now we have more structure on this instances, and now what we actually will, what I'm going to show you later on is actually a SNARK for a particular kind of batch NP language, which is what I call batch index language. So here there is one circuit C that is fixed, and the instances are just these indices I. And in this case, we will build a SNARK for batch index where the verification time, is just polylog T. So there's no additive T term or anything.
So can you actually extend this to the setting of incrementally verifiable computation where you have a
I will
secret?
talk about that towards the end. That's like, more recent work. I'll mention that towards the end, not by me. Okay. Okay, so this is the way to overcome the issue of the verifier running time being potentially linear in capital T. So this is how we will avoid it.
And this is of course inherently computational. And you said it in the information theoretic setting. We know that we cannot do it for P in proofs, right? And for UP, for a batch NP, it's still open.
It's still open, yeah.
So potentially there is such information theoretic reduction, which would rule out proofs for batch NP. Will rule out extending batch UP to batch NP if such a transformation could be made to work. My question is, do we know if there is in the setting of proofs a similar transformation from batch NP to
P?
This would rule out. This would give us a negative.
I see. Yeah, a negative result for batch NP. Okay, that's a good question. I don't know.
Yeah, this approach is inherently.
Yeah, this is very computational. Yeah, that's a good question. Though. Yeah. Okay, so that was the issue of verification time, which again, like I said, I basically just deferred to later. With a new problem statement about SNARKs for batch index language. So now let's talk about soundness, right? So how will we argue that this is sound? So again, the natural idea here would be that, so our CRS will contain the SSB key, the key to the SSB commitment, right? Which we can program at various indices. And the natural idea would be to, program it at a pair of consecutive indices at a time so as to extract those states from the commitment, reason about valid transition, and then keep on progressing further from basically from the start till the end of the computation, right? So initially I could start with the I star and I star plus 1 for some I star, and then go from I star plus 1 to I star plus 2, right? And try to progress. So one thing that I have to be careful about is that, there's this is a sequence of computations, right? These are not independent computations. This is the same incremental computation. So I have to make sure that when I do this switch from SSB key being programmed on I star and I star plus 1 to I star plus 1 and I star plus 2, this, the common value, which is this, what the adversary committed on I star plus 1, doesn't quite change, right? And because if it did, maybe I cannot argue anymore that the start, it's the same sequence of transformations. Okay, so this is actually not a new problem. This has been studied before in the designated verifier setting. If you're familiar with that literature and know about no signaling PCPs and so on, then you know the way to solve this problem. In our work, we use this notion of no signaling SSBs, which is again very, very similar idea. The intuition is essentially the same. What it's saying is that you can consider a notion of SSB where the key can be programmed on a bunch of indices. So let's say either S1, and in the other experiment, it can be programmed on a bunch of indices S2, sets of indices. And what we want is that the indices in the intersection, right? When you apply the extractor in the first case or in the second case, the values in the intersection don't quite change. That's the requirement. Why is it called no signaling? That's not my name, but it comes from the literature on no signaling PCPs, I guess. Presumably that's the reason for the name.
So wait, if your SSB hash is just binding on, like, it just consists of a bunch of pieces where you're binding on one location in each piece, you just get this for free. Right? Yeah,
exactly. I mean, that is essentially, it's just, I mean, that's the construction. What Alex is asking is that, don't you get this property very easily? And indeed, you can use the name or you can ignore the formulation and just prove this property in line, which is essentially this transformation. You just take a SSB and many copies of it and you get this property essentially very easily.
Confused. These are two separate independent experiments.
Mm-hmm.
So
either
the scene may just be totally different, right? The commitment may be totally different.
That's fine. I mean, so what we are asking for here is that sorry, just a second. What is
But you fix the adversary.
Yeah. Sorry?
You fix the adversary.
Right? Yeah.
There's some implicit distribution of messages that it has in mind, presumably. Right. Presumably it's the same distribution, regardless if I give you KS1 or KS2.
Yeah.
Oh, okay.
Yeah. Okay. Okay, so now that we have this, now we can actually do that, proof of soundness. And now I'm using the more familiar terminology of local to global consistency, right? So again, the point was that by using SSB extraction and the soundness of batch SNARKs for batch NP, we were arguing about correctness of one step of this computation at a time, right? So initially we argued that, the first step is correct. And then, we changed the CRS. And now we want to argue that the next step is correct. And here now we are going to rely upon the no signaling property to basically say that the extracted value corresponding to the second state, it's still basically leads to it's still consistent with the starting point, and it will lead to accept. So you can now keep on progressing further and further until the end, and you will argue overall soundness. Right? So again, the bottom line here is that if you think about batch NP, there all the instances are completely independent, right? And whereas in P, when I reduce P to batch NP, the instances are related, and therefore I need to reason about all of them together. And because the proof is small and the soundness property of batch NP allows me to only reason about one small portion of the computation at a time, I need to tie them together, and that's what this no signaling property is giving me. Okay. And again, this is very analogous to what was done in the literature on private delegation. In fact, there is an alternative transformation from the work of Yael, Vinod, and Rachel, which Rachel or Lisa? Rachel, yeah. Okay, sorry. Yes, which basically gives which actually just uses no signaling PCPs to to go from batch NP to P. And one nice thing about this alternative transformation is that it basically gives you, shows you a way to go from batch NP to any subclass of NP for which you have no signaling PCPs. So for example, you can get bounded space NP also just generically from this transformation, whereas if you were to try to obtain bounded space NP from the transformation that I showed you, you will have to reason about it again, basically. And one point that I want to mention is that essentially the main technical barrier, when you want to build SNARKs for any any class, right? The main technical barrier almost inevitably turns out to be finding a way to go from local to global consistency. And I'll revisit this point towards the end of the talk. When did I start?
We started at 2. You can have a little bit, maybe 4 minutes after 3.
Okay, so I'm going quite slow. Okay, all right. Okay, so now the next step is, okay, so we did the transformation from batch NP to P, and now the remaining task is to build SNARKs for batch NP. And even there, like I mentioned, I'm only going to focus on building the interactive protocol. Compressing it to a non-interactive version is not something I'm going to talk about. Okay. So the goal is to build dual mode interactive batch arguments. And the recipe for this is very, very simple and very natural. Basically, think of Killian, except that now instead of proving one statement, I'm trying to prove multiple statements. So I will take the witnesses for all of these, let's say capital T statements. Okay, and I'm going to prepare PCPs for all of them. But now instead of committing them in the way you commit to them in Killian, here I'm going to actually commit to them column wise. Okay, so again, if you think about let's fix some terminology, right? So the number of instances is capital T. Okay, the size of the PCP I don't really care. It's some polynomial in the witness size. Okay, and if you remember, the efficiency requirement for batch NP is that I am okay with paying communication polynomial in the size of one witness, but I don't want it to be witness times the number of instances, right? So if I commit to all of these PCPs column wise, right, then my total first round message that I'm going to send is essentially going to be these SSB commitments, which is polynomial in the witness length. Okay, and logarithmic in capital T, which is okay. Okay, so that's the first round message. Now the verifier can send me PCP queries, and now the prover will basically open the columns. Okay, so imagine the PCP queries are essentially the same for all the instances. Okay. So now I just go to those particular columns and I just open them. Okay, so that's the starting point. Now the verifier will essentially verify all the SSB openings and then the PCPs, right, for all the instances. So okay, so here you can already see. Okay, so actually before getting into the issues with verification time and so on and so forth, let me just say that if you buy the structure of this protocol, then proving security is also going to be very natural. If we want to prove this dual mode security, we can switch the SSB key to one which is binding at one particular index, and that will allow me to basically be binding at one entire row, which will allow me to extract that entire PCP out, and then I can argue soundness. So that's not a problem. The main issue here is really efficiency. Okay, so if you look at this construction, what is the verification time here actually? Well, the verifier is actually reading omega t values, right? Because each of these columns itself is size capital T, right? So therefore, the verification time is not what I want. It's not polylog T. Okay. So the idea here is that what we will do is that instead of asking the verifier to do this verification on its own, we will ask him to basically just delegate this verification process to the prover itself. Okay, so you can think of these these columns, right? So you can, first of all, you can use SSB with local openings, right? And now I can look at basically, capital T verification processes, right? And now I can just define this as a new batch language, right? And I can hope to run another SNARK for batch index language, right? And then basically now the prover can give this proof, and hopefully this will reduce the verify time. Okay. So that's the idea, right? So what is so if we started with basically T instances, right? Now I'm asking the prover to give me another SNARK, right? For a batch index language. How many instances are there? Well, it's still capital T, right? Because I didn't really do anything as is, right? The verifier needed to verify T openings and T PCP, right? And I'm still doing the same thing, right? So we haven't really done anything, right? Ideally, we would like to have some saving in this step so that then we can do some recursion, right? Okay. So what I'm going to do now is start grouping these instances into fewer number of instances to have some saving in the instance length, and then I can, recurse. Okay. So let me try to speed up through this a little bit. So first of all, what I can do is I can define a new relation where instead of verifying, one instance, I'm verifying 2 instances at a time, right? And we can use the structure of the instances here, right? So the instances are just these indices, right? 1, 2, 3, 4. So instead of 1, 2, I can just write 1. And from that, I can derive basically, 1 and 2 on my own, right? This can just be part of the verification algorithm. And similarly for the next one, right? So now just with this simple utilization of the structure of the instance, I now have T by 2 instances. Okay? But we're still not done, mainly because the verification time, right, is still actually twice what it was, what it was in the single case, right? Because the problem is that we are actually performing 2 verifications, right? And if you just use standard PCPs, what is going to happen is that the verification algorithm will be at least proportional to the size of the circuit, right? Which is the circuit that we started with. So now when you do this batching, the verification time of the new batch relation, right, is actually 2 times capital C. Simply because each of these steps here involves basically performing 2 PCP verifications, right? So now we have 2 times C, and now you can see that if you recurse, it will start blowing up. And at the bottom level of the recursion, you will have T times capital C. Again, no saving at all, right? So basically, the final trick is just to use PCPs with this offline online property, where the idea is that the PCP verifier can first use the circuit description to produce queries and a small state, a compact state. And now there's a decision algorithm, an online decision algorithm, which depends on the instance and that succinct state, and then outputs accept or reject. But the running time of this decision algorithm is just dependent on the instance length, not on the circuit size. Okay. So now if you have such PCPs, then it's, the idea is fairly natural. What we will do is we will run this query generation algorithm once and for all, and then just keep it outside the recursion. Right? In the recursion, this query generation algorithm doesn't happen. Only the decision algorithm shows up, which is fast, and therefore now we don't have any more blow up. Good. So that's essentially, all I wanted to say about the construction of SNARKs for batch NP. So this gives you batch index. From batch index, there are simple tricks to get general batch NP, and from there, I already showed you how to go from batch NP to P. Okay. So in terms of cryptographic assumptions, right, why does LWE show up? So it shows up in 2 places. So we are using SSB commitments with local openings. Those you can actually build from a variety of assumptions. So that's not really the crucial LWE part. The crucial LWE part is the CI hash function of Alex, Justin, and Ron, which I didn't really touch upon. That one we only know from LWE currently. And this is why this result is crucially using LWE.
Or IO.
I mean, this particular transformation is using. Actually, is there any version of your result, Alex, from IO?
So it's a little complicated. Well, first of all, IO won't give you like SSB type things, right? So you'll have to make an additional assumption for that.
I see.
But then for just the correlation and tractability, you should be able to do it.
Okay. Okay. So let me use the last 6-7 minutes. Okay.
Wait, but ignoring this approach, just SNARKs for P with full adaptive soundness from IO, is that known?
I think that is known. Isn't that known from our version of our paper, Rachel? SNARKs for P with full adaptivity from IO. I think from at least from sub-exponential IO. I think that is known.
Yeah, probabilistic time.
Yeah, from the from the IO for Turing machine approach. Yeah. Okay. So let me now talk about some more recent work that happened subsequent to these works and some open questions. So first we can ask the question about assumptions again, right? What assumptions do we really need to build these objects? I showed you that we can build them from LWE, but it's obviously natural to ask, can we build them from other assumptions, something other than LWE or IO? So there are some results that are known in this regard. So first of all, even in the work prior to the work that I presented, we did show some constructions of SNARKs for batch NP with very weak succinctness, not quite strong enough to obtain SNARKs for P. And there, the assumptions we used were basically a combination assumption, QR and sub-exponential DDH. And again, the exact combination is not that important. The main point is that we are basically beholden to what kind of CI hash do we know. And then, from what assumptions do we know CI hash? And then that dictates basically what assumptions we are using here. And then subsequent to the work that I presented, there was a work by Pillet et al., which did give better efficiency. So SNARKs for batch NP and P with sublinear succinctness, again, not polylog, but sublinear succinctness from the same assumptions, QR and sub-exponential DDH.
What's the difference between weak and sublinear?
Yeah, so weak is that there we actually have like linear in the K term, but it's not like K times C, it's like K plus something. Yeah. Okay, so in terms of if you want to follow this particular approach of using CI hash to build SNARKs, then one natural pressure point is what kind of assumptions can you build CI hash from? And the current technique seems to rely upon these strong tools, compression tools like FHE or trapdoor hash, etc. And it's not, we don't know to what extent are these techniques necessary. So that's a question of independent interest, even if you don't care about SNARKs per se, because any progress on this front would also lead to progress on NISIX from other assumptions and the many applications of CI hash. Okay. Another question you can ask is, well, must we use CI hash, or can we use this Fiat-Shamir plus CI hash approach altogether? That would be great. And there is, in fact, really cool work by Brent and David recently, which shows how you can get SNARKs for batch NP and P from typo here, yeah, from bilinear maps. One really cool part of this is that it doesn't use PCPs at all, right? I think the only slight caveat that I know of is that the CRS size is sublinear rather than polylog, but it doesn't show in the verification time because the verifier doesn't need to read the entire CRS. Only the prover reads the long CRS. Okay.
So it doesn't use even linear PCP?
No. Yeah, so this is, I mean, the cool thing about it is it's a very natural, you can think of it as essentially taking the non-ZK version of GOS and batching it, and then batching it basically, yeah. So both the commitments, as the gate-by-gate commitments, and then also the proofs, batch proof for. So you can ask the question whether it's possible to mimic or somehow adapt their approach to LWE so as to avoid the use of PCPs altogether. That's a great open question. Okay, couple of words about efficiency. So you can ask the question, can we build these SNARKs for these particular subclasses that I talked about, in particular batch NP, with better communication rate? So the solution that I presented, the size of the proof is essentially poly log in k comma, sorry, poly in log k comma w, right? So it can, right? Whereas you could hope for something much, much better, which is essentially just the size of a single witness plus some additive terms, right? That's not achieved by our solution. And the cool thing about achieving such a nice rate is that it naturally leads to many nice applications, because you can start composing these proofs. You can start, proving things about proofs and so on. So you can do, for example, incrementally verifiable computation, which the question that Stefano was asking. And there is a recent cool work that I'm aware of by Rishabh, Yael, and Vinod, which does give a solution to this problem. I think assuming LWE. Oh, okay, yeah. Okay, cool. Okay, I'm going to skip this this point. Okay, so maybe I'll take 2 more minutes. Is that okay? Yeah, yeah. Okay, so I think perhaps the most interesting open question is obviously, can we find a way to circumvent gentrifics, right? Okay, so a word about gentrifics. First of all, what does the statement actually say? What does their impossibility say? So it basically says that you cannot have you cannot build SNARKs for NP where the proof of soundness is black box. Okay, so it makes black box use of the adversary. Second, soundness is adaptive, meaning that the adversary chooses the instance after looking at the CRS. Okay? So these are the 2 main requirements. The third one is just a technical thing. So what I mean by this L greater than Y is that basically it requires that the language is harder to decide than the assumption, basically. So in other words, the reduction cannot decide the language, right? That's a technical requirement in the lower bound. Okay. So there are these ways of, so basically these restrictions also obviously potentially pose a way to, potentially pose a path to try to circumvent this lower bound. Black box reductions, we don't know of many examples of non-black box reductions. So perhaps that is a harder route. Perhaps the most tempting, path is to try to achieve non-adaptive soundness, right? So what do we know about this? Again, even here, the main challenge turns out to be this local to global consistency. It would seem that in the non-adaptive setting, perhaps this is not so much of a challenge, but it still shows up. We still don't know how to overcome this. Again, the proof techniques always do this thing of arguing correctness of subcomputations and tying them together. And we only know how to make this work for various subclasses, but not for all of NP. Of course.
Is this question any different from that? Like, are you separating this question from the question of whether you can build no signaling PCP?
Not really. I mean, yeah, not really. No. Yeah. Is this question any different from construction of no signaling PCPs, computational no signaling PCPs?
But you're asking the question of go beyond no signaling PCPs, right?
I mean, but we don't know of any barrier to computational no signaling PCPs, right? That we can't build them for. Is there any lower bound?
Computational no signaling PCP is even a stronger object than no signaling PCP.
Yeah.
So they can only exist for, I don't know.
No, but do we have any lower bounds there that we can't?
Yes, no signaling PCPs with communication L can only be for languages decided 1 times 2 to the L. Something like that.
Yes, beyond P is sort of a problem.
Okay, and then perhaps the natural question is, what about I/O, right? Can we use I/O to build non-adaptive SNARKs for NP? And indeed, we know of a result, right? So we know this high waters construction, which gives you SNARKs for NP. There's a large CRS involved there. Let's ignore that caveat. And now, you can instantiate that construction with, let's say, GLS, and you get SNARKs for non-adaptive SNARKs for NP with the corresponding assumptions. Okay, so one last slide, I'll just mention, one caveat of this result, right, is that if you actually take a closer look at what happens when you instantiate the Sahai-Waters construction with the JLS, or in fact any other IO construction, what would happen is that in some sense it bypasses Gentry-Wicks, irrespective of the fact that the soundness is non-adaptive. It's because what happens is that the hardness requirement flips. Gentry-Wicks says that the reduction should not be able to decide the language, right? But when you instantiate IO, because of the IO input length barrier, which is that the reduction always seems to incur exponential loss in the input length, what happens is that you end up requiring that the assumption is actually harder than the language. In other words, the reduction can actually decide the language. Okay, so this sort of happens. So you can ask a question if this can be circumvented, essentially. So I won't mention too much, but there is some progress on this for subclasses of NP, even subclass of NP intersection co-NP. It's there are several caveats to this result, but there's some progress on this front, which I can talk about offline if somebody is interested.
If you relax on SNARKs for NP, where the proof length is input size as opposed to witness size, so we don't want full succinctness, do we have any barriers?
What was the question again?
If the proof length is instance size, not witness size, you allow the proof size to grow with the instance size. Do we know anything about that?
It's a good time to leave this to the discussion of the break.
Okay.
And we'll reconvene at 3:30.
Okay, thank you.